Hello everybody, welcome to this course about the Expressive Vector Engine, the EVE library. I'm Joël Falcou. I wish I would have been able to be with you in person, but unexpected health issues stranded me in, so all my excuses for not being there. A small bit of logistics about these pre-recorded courses, so everything can be, cool for everybody. We are going to have a look at a bunch of things, a bunch of codes. Some of them are in your Docker container concerning Eve, some are not. I encourage you to try and manipulate the library on your own. After a while, we are going to see how it works, how we can compile it, and so on. I will be available on the Discord server starting this afternoon and all week long. So if you want to snatch me and ask me about stuff, issues, or whatever about Eve, don't hesitate. I will try to be helpful on this matter despite the circumstances. A bunch of links are put into the PDF. For accessing some kind of runtime of the examples. They are hosted by on the CodeRecon's learning platforms. So you can have a look at them, not necessarily modify them unless you already have an account on the platform, but it should be okay for transporting the code and the results. Okay. I will stay over there during the video so you can see me, some people like that. And again, if you have any question, I will be able to answer them after this video, starting this afternoon. Okay, so now let's dive into the actual matter. We are going to speak about, again, vectorization, but this time, instead of letting the compiler try to do something, instead of relying on other library, or worse, instead of trying to write SIMD intrinsic by hand, we are going to explore another venue, which is manipulating and writing SIMD-enabled code using some high-level C++ library. So let's start by maybe getting a refresher, because you heard about it, you get some courses already on that, but it's cool to go back to the very beginning about what, how, and why we want to do SIMD programming. And first, what is actually SIMD programming, okay? So let's start by something else. Let's start by speaking about SCISD. So SIMD, SCISD, and you probably also heard about MIMD, are all nomenclatures from the Fin classification that basically dispatch parallel system into different categories based on the number of instruction stream and data stream the machine is able to process. An SISD machine, it's a single instruction, single data machine. Okay, so it basically runs one stream of instruction over one stream of data. Stuff happens somewhere in the processor or whatever, and you get one result. And every so much cycle, a new instruction goes in with data or a bunch of data, something is computed, and we got a result. Basically, whenever you use a single core of your processor without doing anything fancy, you are basically running on a SISD machine. It's a bit more complicated than that, and I see people over there in the back. It's a bit more complicated than that because sometimes a modern CPU can take the liberty of running some instruction out of order to split an instruction into simpler one, or other tricks like that, being super scalar and whatnot. But in the end, we can simplify all of that by having this step block, instruction stream, data stream, and we get a result stream. And at some point, somebody came up and said, okay, that's a bit wasteful because I have a bunch of transistors I don't use. Okay, it happens sometimes. So maybe I can have registers which are larger than usual. And instead of fitting inside more bits for an integer or more precision for a floating point value, what about we put multiple value inside those? And that's what SIMD is actually. We still have a single instruction stream, okay? But now the data stream is actually multiple value per instruction. They are usually stored into what we call wide registers. Those registers contain value in different lanes. And the idea is that those instructions operating on those data produce the same amount of results with a cost in cycle which is basically roughly the same as the SISD machine. And so what we expect when everything will be okay, what we expect is to get a speed up coming from the fact that the registers are wider than regular ones. If I consume and produce 4 integer results per cycle whenever I do, I don't know, like a complement, a bit complement, instead of processing 1 integer per cycle, I expect to go 4 times faster. And again, I will put some emphasis on that because I know it's complicated and there was a lot of question about that last week. This is not multiprocessing. This is not multi-threading, okay? This is inside a single core of your processor. So SIMD is basically a source of performances that come from the fact that in a single core of your processor, multiple operations can be applied on multiple data at the same time every cycle. And this is where we want to grab some additional speed up. And as it's inside one core, it's composable with the fact that you are going to run OpenMP on top of that, and you are going to run MPI on top of that. It's an additional leverage of performance in the end. It's a very low level one, and we have to be careful about what we do with that. It's tied, performance are actually tied to a lot of other factors we are going to discuss, but if we put that into perspective, it's basically just using some subtop registers that already live in your processor, and that most of the time, unless auto-vectorizer come in, nobody is actually using. Okay, fine. But what are those registers actually? As we said, SIMD registers are organized into what we call lanes. Okay? A lane is basically a single value inside the whole register. But whenever we apply an operation on a SIMD register, the same operation is in parallel applied to each lane, each value inside the register. Depending on the architecture, x86, ARM, PowerPC, and even in a single architecture, depending on the flavor of SIMD extension you want to use, you have more or less lanes per SIMD register, and you have more or less the same family of type inside. Some architecture doesn't support double, some doesn't support 64-bit integers. Well, nowadays they all basically support everything, but it's not a guarantee. And so if we take the example of the x86 SSC extension that use 128 bits registers, we see that we can look at them as either a pair of 64 bits element, double or long, a quadruplet of float or 32 bits integer, a pack of 8 16 bits integer, 8 short or 8 intermediate short, and 16 8 bits value. And we see that quickly 8, 16, that's basically one order of magnitude in terms of performance. If I was able to get a X10 on processing 16 char each time I use those kind of register, it's a massive win. I jump one level of magnitude. And that's only the 128 bits version. We are going to see that we are 256, 512, or even 1024 bits register. And each time we double the size of the register, we have more and more value per register of the same type. One thing we need to be careful about that at some point, we cannot just continue and make those registers grow, because at some point, if your register is bigger than your cache line, you will have some issues. But CPU vendors sort of know about that. So yeah, so we have these multiple things. One very easy way to get around that is to see a SIMD register as a small, hardware-based, statically sized array. That's a very crude simplification, but it's basically this. Okay. So now, what happens when I try to make some operation on that? We can visualize this way. If you do an addition between two registers containing 8 value, let's say it's 8 shorts, what happens is in a single pass, we are going to have those 8 results computed directly into the results. That's where the performance speed up lies. The fact that we can do all of that basically in the same time, the same space, that we can do a single one. So now, we said that we had a bunch of different architectures and extensions. What are we actually talking about? We basically are thinking of this. The first SIMD extension set came from the the late 90s, early 2000s, with SSE and VMX that we also known as Altivec. And as we see, as time goes, the number and the variety of SIMD extension just keep growing. Okay, so we have all the SSE variants that are all the x86 Intel 128 bits register extension. That got replaced by AVX, AVX2 in the 2010s, that are 256 bits instructions. And then later on, in 2016 and above, the advent of AVX 512, and the name says it all, it's 512 bits registers. But in the meantime, while Intel was running a mock like that, PowerPC with VMX and then QPX and VSX tried to improve. PowerPC is now a bit defunct, but it was also a very good system. The underdog was ARM with Neon that got updated to ASIMD to support 64 bits values, still in a 128 bit register. And it came back into the 2020s with SVE and SVE2, which is a bit different. It's a flexible size between 128 and 1024 bits registers. And at the same time, we got new things like the SIMD for WASM. Okay, so you can have SIMD in your browser now. And RISC-V, which is a big new thing right now that is very similar to SVE and AVX 512. Okay, but what about my machine? How do I know? How do I know that I have this or that thing available? To do that, we have different way of guessing or getting the information about what your machine is actually getting. On Linux, you can either use LSCPU if you have it installed, or you can install it. It's a classical package. Or you can look inside proc CPU info. We are going to get a look at that. If you're on macOS, you can go through the bash sysctl command or the equivalent C POSIX functions. And on Windows, if you are on PowerShell, you can install sysinternals and have access to core info. So let's have a look at what happened on Linux there. So I am on some WSL machine, but that doesn't change. I can actually run LSCPU there. So we got a bunch of information, and what we are looking for stands in the flags part, okay, where we can see that I have SSE, I have SSE2, a bunch of other SSE whatever. Where are you? AVX, AVX2, F16C, which is also a SIMD instruction set dedicated to floating point of 16 bits. And on this machine, that's all. I don't have anything else. We could actually go to some AVX 512 machine. It happens to be there. And if I do it this way, LSCPU, you can see that indeed, well, you know what? It's a lot of things. So let's grab a bit. Okay, what flavor of AVX 512 do we have? Yeah, a bunch. Okay, we are going to see how it works. But I have AVX 512. I got obviously all the other, and so on and so forth. If I do proc CPU info, what do I get? I get basically the same thing. It's the internal elements of what we got with CPU, LSCPU. So we can have those information. If you want to have those information at runtime inside your program, you can use a CPU ID or some variation thereof. It's a low-level instructions. It's a bit complicated to use. We are going to see later that we have a wrapper for that. So you can actually get access to that at runtime. Okay? So there is a lot of different instruction sets. Okay, that's the first information. But the question then is why I want to double with that, and how do I exploit this? Okay, so maybe you want to go fast. So your first thought could be I'm going to run on GPUs, except some code doesn't fit GPU model of programming. Okay, or you cannot have a GPU for that, depending on your energy budget or your budget alone. And SIMD instruction sets are basically everywhere. If you have a processor that has no SIMD instruction set, it's a machine from before the 2000s. So that's time to, ask your hierarchy for getting a new machine. Okay, you see what I mean. So it's already there. So why not using this X4, X8, X16 speedup? Why should I consume more cores? Why should I jump over a GPU with all the problems the GPU causes, actually? So you see that you can abuse and use a similar instruction set by trying to auto-vectorize manually. You can use OpenMP4 pragmas. You have special compiler like ISPC that can do the job for you. There is some libraries that wrap some standard looking algorithm. You have the STD execution that do some, HPX also do some, or you can use specialized tools. You do image processing, maybe have a look at ALID that provide you a domain-specific language that take care of this vectorization, among other things. You are dealing with JSON file and you want to go faster, maybe have a look at SIMD.JSON or some other library like that. And sometimes you won't find what you need, and you are going to write some SIMD manually. And that's the point where normally I should play some dramatic music, okay? So imagine, okay? So yeah, doing manual SIMD is something that is both alluring and terrible at the same time. So SIMD programming use intrinsics, which are basically small magical functions that the compiler recognize, okay, and turn into the actual low-level assembly bits that do the manipulation of the of the SIMD registers. It's very direct. You basically generate a single or a couple of specific machine instructions. But to use them, you are going to use specific data types that are usually ugly types, let's say it this way, that doesn't behave like you want, that needs to be wrapped somehow, and you have to remember what you do with them. So intrinsic will provide the operations, okay, on those intrinsics. As we are going to see, it's not that easy, actually. Okay. Sometimes you have most of the time, functions that are dedicated to loading data and storing data between the main memory and SIMD register. One very specific behavior that we have whenever you want to write your own SIMD operation, SIMD algorithm, is the fact that most, if not all, memory movement back and forth from the memory to the register has to be explicit. And we are going to see that, yeah, it's a mouthful sometimes, let's say it this way. But in practice, well, what do we get from that? Well, you get maximum performance, and people like that. You are writing exactly what the CPU should be doing. You are going to fully utilize whatever the CPU is giving you in terms of registers and complex operation. You are going to go fast. Under the pretense that you are going to understand what you are going to write. Yeah, you can manage the very minute details of your implementation, where and when the memory is accessed, how many numerical tricks you can apply that will help you go faster and whatnot. At the cost of a limited portability, because whenever, we are going to see that right now, whenever you use one of the specific, how to say that? On the specific size and whatnot, okay? You are going to have to think a lot about a slew of complex algorithm and structure of your code. Okay. Next to that, you are also going to know exactly what the architectures you are targeting is able to do at this level. Because as we said, we don't have every operation on every instruction set. And sometimes you are going to do, well, you have to be creative. And to understand this, let's have a look at the actual subset of intrinsics we can get. You know what? Let's just do something simple. Let's go have a look at x86 intrinsic list for SIMD programming. Okay, let's zoom a bit. Okay, so this is the Intel Intrinsic Guide web page. Okay, that basically lists, as the name implies, all the intrinsics for all and every SIMD instruction set that x86 is providing. And as you can see, with this very, very pragmatic measure of, well, the size of the slider, yeah, it's massive. Okay, it's I don't know how many actually. So let's focus. Let's just focusing on the 128 bits family, right? Yeah, it's still a lot. Still a lot. Multiple issues, as we said. We have those funky types. __ M128i, M64, the 128, 28D, and whatnot. Okay. So basically, well, it's not that complicated. 128i, it's an integer register. 128, it's a single precision floating point register. With a D, it's a double precision. Fine. And then you have the naming scheme of the function. Some are okay. I mean, I kind of guess what this is doing. It's probably a vectorized version of 16.4 bits absolute value, addition, and whatnot. Add sub, what? I'm supposed to do the same thing on both. What is that? Line R, AVG, blend, my favorite BSRLLI, okay? And it starts to be a bit complicated. Okay, some have ugly things. But let's see, do I have, like for example, how many multiplication do I have in SSC thing, multiplication? Yeah, multiple. So we have some things for the 32 bits, sign or unsigned, for the floating point. And that's all. I don't have anything for less than that. Oh, well, you know what, maybe I can have a look at division. Oh, that only exists for floating point numbers. Or maybe I have like, I don't know, let's have a look at absolute values that only exist for some integer size. So we have alls. And whenever we go up a family, you see that they get completed. So that is now the AVX intrinsics, okay, on 256 bits. Now the name of the register change, this also change. And if I keep doing this, AVX512 also, and it has like a lot of them, okay? I just want to make an absolute value why I am supposed to look at this massive list. I don't know what to use, and some of them are actually not what you want. And sometimes you have, I mean, you can load data. Let's focus on AVX512, for example. You can load data somehow. Oh, yeah, maybe I can add data somehow. Okay, even that starts to be very complicated. And sometimes you have a funky thing. Where are you? Where are you? No, it's not. Oh, field. Oh, okay. Is it not there? Oh, come on. Yeah, G something. 512G. Where are you? Oh, come on. Okay, there is some fancy things going on. Okay. Yeah, a bunch of things. You can do a lot. Okay, it's not there. Oh, maybe it's not there. Let's try to. Yeah. You have wonderful things like this, okay, which is obviously, as the name implies, the computation of an affine transformation is a Galois field of 2 to the 8th, which is defined as a x times x plus b operations, where you have an 8-bit matrix and an 8-bit vector that gets stored into an 8-bit packed result. If you didn't understand a word of what I just said, don't worry, neither do I. Okay? That's one of those very obscure functions that are just there, while in the same time we don't have the basics like absolute value for floating point numbers. So we have this very wide set of operations, and sometimes we lack the basics. Oh yeah, but maybe that's Intel, you know. I mean, you know how they are. Okay, so let's go to the ARM intrinsic list. Maybe it's better. Yeah. You can have a look at the 4,344 different neon functions. Let's say I'm only interested in the floating point computation. That's still 834 functions. Okay, let's say I'm only interested in 32-bit floating point in the modern system. Yeah, still 300 and something. So we have the basic, we have add, and we have mul, and we have mulex. Okay, and mulex lane, and mulex lane q. Okay, and you see that we are back into, the international contest of how can I name my function so people have no clue what the heck they are doing. And I am supposed to know that, okay, to look at this kind of documentation where, I mean, I don't even know what I'm looking at. And I'm forced to do that? Yes. Yes, you are. Been there, done that, 0 over 10, don't recommend, okay? You want to do a times b plus c, right? With 32 bits integer? Well, in SSE2, good luck, you have no way to do that. That fit into a slide. You have to combine arbitrary whatever in SSE4, and if you go on PowerPC, you have that for floating point number, so you have to convert everything into a floating point number, do the computation, go back to the integer. ARM, well, you have it. You have a vmul E32. Done. Other extension, you don't know. And that's just a times b plus c. It's not even a big thing. Okay, right? As soon as you go upper than that, you're basically on your own trying to reconstruct basic operations. You want to do trigonometry? Well, sad to be used, there is none. There is very few transcendental functions. And when they exist, sometimes they have very poor precisions. And so, for having been through that back in the day, I mean, 80% of what you should know about SIMD programming by hand is to try to find a way to know the tricks that people from the 2000 discover by accident, transmit by oral tradition, including, visiting them on the top of some mountain during winter or whatnot. So you know what exact incantation you should put into this so that it makes sense to the CPU. And I speak about a lot of ugly tricks. We are going to see a bunch of them at some point, and you don't want to know about that. You're here to do some physics computation. You are here to do some statistics, and so on and so forth. So the question is, why, are those things not so complicated? Well, because the emphasis has been put onto whatever the hardware is supposed to do, and the high level, the user-facing interface is often an afterthought. It has to go to some intrinsics, it has to generate the proper compile time, whatever. But how? Well, I don't know. Somehow. Okay. So this is a bit infuriating, okay, because I just want to compute some stuff. Okay. And I'm forced to deal with that, spend some time in documentation that even if it wasn't there, we don't know if we could see the difference. So it's verbose, it's difficult, it's non-portable. God forbid you have to support two different extension sets. even on the same architectures. So often people just pick a choice, pick an architecture, and they say, oh yeah, we optimize for that. The rest, I don't know. So sometimes what you want to do is to use wrapper libraries that are more user-friendly because they do all these preemptive tasks of gathering the information about whatever kind of tricks you need to put into your code so it works. And actually expose that into an API that makes some sense. Sort of. There is a bunch. I'm just focusing on some that you maybe know already, or they are, I mean, whenever I make a paper, I have to cite them, so they are somehow important. Highway, which is developed by Google, it's a wrapping library that use the use of macro and reentrant code generation. It works. As usual, caveat, it's a Google library. It exists right now. Will it exist in a month, in a year? I don't know. You have SIMD-E, that is just a compatibility layer that lets you write any intrinsic from any extension into any others, and the library just polyfill whatever you miss. So if you have a code using SSE2 that uses SSE2 intrinsic, you can port it to ARM, use SIMD-E, and SIMD-E will replace the intrinsics, the SSE2 intrinsics by the corresponding ARM intrinsics, and you will see nothing. Performance are not guaranteed because sometimes you don't have a one-to-one, correspondence, but it tries to make it work. And sometimes it's a good thing because you can just try and get something working. XMD, it's C++ 14 libraries that do classical wrapping, okay, that we are going to see. And starting from a few months now, we have std-cmd in the C++26 standard. How to say that? It exists. That's one of its main selling points. It's still not very well supported by most of the compilers. Some I'm not even sure if we are going to have an implementation anytime. And it's sometimes very crude in terms of interface, but that's my personal opinion, because I'm clearly biased, because I am one of the authors of Eve, which is also a wrapper library for that. It's a re-implementation of something that was a bit long ago called BoostSIMD, and that is basically one of the great ancestors of all of that. Okay, so we just get a new facelift. So yeah, so what do we propose into this? So Eve is based on C++20, and it proposes a library of core types that wraps all what you need to have to deal with SIMD intrinsics. So you are going to have a proper API over those SIMD registers. That makes sense. You have a bunch of algorithms that let you build more complex structures, and we have over 250 numerical functions that we are going to see a bit later. We work on x86, we work on ARM, on 64-bit ARM, PowerPC, even if it's less tested right now because we don't have a machine, but it worked. We have ongoing work for WASM and RISC-V also. It's Boost license, so it's rather, how to say that, permissive. Okay. It's also, and I want to put some emphasis on that, it's a long team effort from 2016 now, 2018. So big shout out to all those people. So Jean Thierry, which is one of the first collaborators we had, Dennis also, which is which was the mastermind behind the rework of the algorithm system. Alexis Owen, Adrien Enro, Pierre Estery, some other of my former PhD students that build or collaborated into implementing parts of this library. So what can we do? Well, you can find us on GitHub. Let's do that. Okay, so we should be, oh, where are you? Okay, so we are somewhere on GitHub. Yeah, gfalco/eve, okay. Click on the star, we like that, make forks and whatever. So you can just clone ourselves from there and you get basically whatever you need. we have a somehow extensive test system, just so you know that we care about the quality of whatever we are going to provide. We have like some documentation tests, randomized precision tests, and I don't know many, architecture set we do with something over how much do we have? Yeah, almost 800 tests, just so we have everything going on. Okay, so we do things. Oh, okay. I make a stupid things. Okay, I'm a professional, but that's what you get by not looking at what you do. Let's go back there. Okay. So as I said, we are on GitHub. You can play with us on different places, and we have some documentation that has a bunch of references. You get a bunch of tutorials if you want, different things. And we have some reference documentation at the user level, at the developer level, and whatnot. So let's have a look at what kind of math do we do. Well, all the basics. We got some complicated math. Okay. Disclaimer, there is function, I don't even know what they do. They are chantilly la preste work, and it do the math. So it works. So we have some special function and whatnot. Okay, you can see that we are some kind of serious library because we have latex rendering into our documentation. But jokes aside, yeah, we have a bunch of those. We have just ending for numerical constants. We got a bunch of triggers and whatnot. And let's have a look, for example, at where are you, cosinus? Yeah, so we have some documentation, we have a bunch of information there, and usually we have an example that you can copy paste or you can run online. And normally, didn't select the proper one, you get some kind of real-time output of whatever test we have there. Okay, so we try to have a welcoming environment at this level, in the sense that we want people to understand what's going on and whatnot. So yeah, this is it. So yeah, so you can find us quite easily normally. In the if you use a container, you have Eve pre-install with a bunch of compiler we like to have, so you can play around with it without thinking about it. Okay, so fine, we do all of that. How does it look? How does it help? Okay, that's the big questions, and where can we go from there? So let's have a look. Let's have a look at how we wrap the things. So the core type inside Eve is what we call wide. Wide is a type that abstracts away a single register by taking a type and a number of lanes that are optional, and turn that into the best single register we can have, okay, to do operation on that. And we have a compile time system that let us isolate those variations so you cannot mix up bad binaries one with another. Next to that, we have an API on top of this, where we have access to the basic operation as operators and also as as functions. So all the basic arithmetics, all the bitwise operations, the basic math like square root, inverse, stuff like that. We have a fully vectorized CMAT implementation, so you can use vectorized cos, x, log, and whatever. We have a substantive set of fully vectorized special function, Bessel function, combinatorials, okay. Different vectorized polynomials evaluation scheme, some operation inside the register, we are going to have a look at that a bit later, and so on and so forth. So, let's have a look at what we can do with that, and in fact, let's start by having a look at the basic CPP file you have in the container. So let's jump into it. So let's maybe zoom a bit. We want to zoom at this point. So this is a very basic Eve files. We are going to dive into more of those, but this is one of the basic things that you can do and check that it actually works, which is actually important. You have access to the main library without doing anything using the eve/eve.hpp include file. We have others, we are going to see a lot, but this is the basic one. So what do we do there? Let's play around. We have defined a wide of float. A wide of float is a variable that will represent, for whatever machine you have, a potential assembly register able to contain the most meaningful amount of floating point values inside it. Maybe if you are compiling for SSC something, we are going to have a register of 4. If you are on the 256 bits, you are going to have 8 floats, and so on and so forth. We are, as we see there, we are initializing it with some lambdas. That is basically a generator construction. We are going to see what it does. If provide a bunch of objects that let you also know what you are doing and where you are doing it. So we have this if current API object that you can compare to some constant that defines architectures. And when you print it, you know for what kind of architectures you just compiled for. Then we can print the content of our wide register directly. We can do some basic operation like an addition, a square root. So let's see how we can compile that. So we support a bunch of compilers. Our preferred one are GCC 14 and above. And Clang how many? Clang 19 and above, if I'm not mistaken. Yeah, 18 and above. So let's start with GCC. So we are going to compile base.cpp. Okay. We are a C++20 library, so we should compile with C++20. We are going to see what happens if we don't. We are doing SIMD, so we are there to get some performances. So big O of 3 is probably mandatory. We need to, we need to find whatever is, wherever your event session is. If you are running this inside the container, like I am not doing right now, it's pre-installed into a user local include, so you don't have to do anything. But in my case, I work with my development system, so I will need to put some, additional thing like this. But it's not very far. It should be there. Okay. But as I said, yeah, a bit more. You don't have to do that because in the container, it's basically there. Okay, so what did I do? I did a mistake. Oh yeah, because it's basic.cpp, okay. So I decided to not cut that, so you get the basic, I made a demo without looking at what I was doing feelings, okay. So let's start to do that. It compiles, okay. And let's run it. So I just compile with nothing. And by default, if you compile with nothing, you are compiling for SSC2 and above. Okay. So what do we have there? If I run this, okay. So let's go around the print. So we are optimizing for what? For x86 SSC2. Okay, so that's the basic 128 bits register systems. I initialize X by filling it with 1 plus I being the index of the current lane that we want to fill. So I should end up with 1, 2, 3, 4, which is exactly what I have. I compute x plus x, which is 2, 4, 6, 8. And I do some square root, and, it does what it does. 1, square root of 2, square root of 3, square root of 4. Okay. So fine. So I know what I do. I get my result. I don't have to think about what kind of architectures I am doing. I have a wide register, which is the best one for what I ask. Eve compilation model is based on the fact that we know statically at compile time which architecture we are going to optimize for. So now if I want to get better stuff, or maybe I can use SCC 4.2. It's a better 128 bits thing. Let's see what's going on. we should not have very much difference, except now I know that I have access to that. This fine-grained support of extensions is made so that we can always find the most optimal, how to say that, the most optimal series of intrinsics to do one task or another. And whenever something does not exist at a given level, we try to emulate them with different techniques that may or may not include doing some preparation works and ending up doing something with lesser instruction set. That's the way we do the thing. So let's see if I jump a bit, because I have AVX and AVX2 there, so I can go on AVX2. I should have now 256 bits per register, so I expect to have like 8 floating point values in my floating point values. And that's what I got. I got larger vectors. And you see how I didn't touch there. I have a wider float, and whatever I compile for, I got the best one. Which is slightly different than what STD-SIMD is doing, where it tries to get to the lowest common denominator. That's one of our biggest differences. Okay, fine. But what can I do from there? Okay, what kind of thing we can do? You can take some time right now, if you want, to play around with basic.cpp, try other operators, other basic function. Maybe we can have, I don't know, like, let's do that, for example. Oh, yeah, let's do this. Let's do 1 minus x, and let's do the square root of x. Yeah, we should end up with negative values. So what does square t root is going to do? Yeah, did I run the correct one? Oh yeah, but I didn't do the correct thing, so it's 1 minus x, obviously. Let's do the complete error thing. So if I do the correct computation, yeah, I got none, because square root of whatever is none. I don't get any asserts, I don't get any exceptions, I don't get any error code. If is meant to go fast, so we make the assumption that you know what you're doing numerical-wise. We have things that help you not do a mistake. For example, we are non-aware most of the time, so we are going to say you that if you get a non, you do something wrong. Okay? Sometimes we are going to see that we have options that will make those errors more blatant. Okay? But we are going to think that you know what you're doing, okay? And we don't babysit you around these edges, okay? So I see somebody in the back, the Rust guys, they are currently trying to probably want to kill me, but that's the way we wanted to get. We are there to get performances. It's your job to do the precondition checks before you run the big kernel you just optimized. Okay, you see what I mean. Okay, so maybe I can do something simple. Let's just take the absolute value of that and see what's going on, right? It should be better now. And it does, obviously, because we computed the absolute value and whatnot. Okay. Now, we spoke about the size of the wide, and we don't need to specify them. But you can also specify those. Okay. There is an if fixed value that can take a value like that, for example, that can be used to specify how many lengths you want in the register. So, caveat now, I'm doing some kind of, it's important, so I'm there now. I'm speaking of this. We are at the 20-something June 2026. Soon, but I don't know how, when yet, but soonish, probably during the summer, we are going to have a massive ABE breaking changes where fixed disappear to be replaced by just the numbers that is handled differently. So whatever you saw right now is from the pre-simplification PR that maybe is going to come up soonish. Okay, so if it doesn't work, if you look at this video later, this is why. And I'm going back up there. So you can do this. But what happens? Well, let's see what's going on. I can still compile with whatever instruction set I want. And I get the correct things. But what happened? If at compile time is able to take this pair of information, the type and the size, and pick the correct one. So if you compile for AVX2, but you want 4 lengths wider float, you end up with a SSE 4.2 register. Because that's the best way to represent that. Okay, what if I go very low in size? Does it make sense? Well, it does. At least the compiler is happy with it. Okay? And it works. In this case, what we do is that we still use the smallest SIMD register we can find, and we just ignore a part of it. Okay? But what if I ask for more? For example, twice the size I should have. Well, guess what? It also works. And let's guess. Okay, let's guess what happens there. Okay, so I should have a jingle at this point. What do you think happens? Small, small silence if you can pause the things right now so people can express their opinion. What happens is, whenever you have a bigger wide that your hardware is able to support, we are going to basically slice these big things into the biggest chunk we can have. So on AVX2, this thing is actually internally a pair of AVX registers. And Eve know how to handle those aggregation, like we call them, as if they were native registers. Okay, so what's the limit to that? Well, the limits are rather easy. Your lane count must be a power of 2. So if we do that, okay, let's take some space there. So if you do something nonsensical like this, yeah, we got some errors. Okay, we got some errors. Let's bypass that. Because we have a static assert, and then we have like cascading error. But basically, yes, cardinal must be a non-zero power of 2, which 7 is not, clearly. Okay, so we won't let you compile stuff like that. And that's very important to understand that a wide represents a register. It is not some kind of fancy array. It cannot take arbitrary size. And you know what else we do so people doesn't get confused with that? Well, this is not, this is not a valid API neither. We don't have that. Oh, yeah. If I compound the error, it won't work. Let's go back to 8. Let's compile again. Yeah, we don't have that. It's not an array. Sometimes, however, you want to access a one lane of something, and then you have to use the verbose get function. Yes, it is verbose. It is done on purpose, because if you let people manipulate a similar register like array, they write bad code. So one philosophy we have in AIM is that if it's not for you to do, we just don't let you do it. Okay. So that's part of how we work. So we saw that we have a bunch of ways to initialize our wide. Let's have a deep look into this. So you can load data from some place in memory. So we load from an array there. You can load from the dot data from a vector, from a span, for whatever. By default, load performs unaligned load, which is the easiest way to do for users. And we have a notion of align pointer, aligned PTR, that you can use if you want to force the alignment of your load. But most of the time, you don't really care. Modern hardware just doesn't give a crap about, alignment and whatnot. Okay. So you can load from memory. You also have a store function that we are going to see a bit later. You can initialize a wide with a constant Okay, so if you want to put zeros or whatever. By default, if you don't put anything into your while, and I'm sorry for the guy that doesn't like undefined behavior or the one guy over there that do Rust, if you don't initialize the while, we don't put anything inside. You get an initialized variable, and well, you should check that because we are not responsible for the crap you put into your register. We do that so that we can maintain a high level of performance. So we can do that, okay? And you know what? Let's run this actually somewhere. We can play around easier in an easier way. So we are now running this code over our coding platform at CodeRecons, okay? Okay, maybe we should be using, yeah, it was compiling something else. So let's go back to this. Okay, so yeah. So we are compiling for AVX2. So we load the 8 values there. 0 is full of 0, and 4.5 is full of 4.5. Okay. And as I said, okay, let's see if the compiler is actually making me a liar. Okay. Yeah, thanks Clang. Okay, Clang is probably cleaning up the register or whatnot, whatever. Yeah, okay. So obviously when I want it to fail, it won't fail. You know how it goes. Okay, fine. So we can do that. We did float there. Obviously, we can have other types. Okay, we can have that. Okay, it's probably 0 there. And yeah, it has to be integers. Okay. So we know how to detect those things. Obviously. Okay, now let's do something interesting. What kind of code are we generating when we do that? It's a bit complicated to see in the assembly, so let's put that into a function. Let's call that getRegister. Okay, let's take it a pointer to an integer, for example, and let's just return that. Okay, that's what I get for not looking at what I type. So I can do this. So let's have a look at what kind of assembly we got. And in this case, we're probably going to go back to Clang, which has a better thing. No, it does not. Okay, so let's go to GCC then. Yeah, so what do? We take the pointer and we load a YMM register, which is a register we use whenever we are in AVX2. If I'm going back to SSE 4.2, the code automatically changes. And now we are going to load into an XMM register. Now, if I deactivate the execution because I do not have an AVX512 machine, and I ask for some of those, so for example, let's say Sapphire Rapids, with a proper number of P. Yeah, now we are loading up into a ZMM. Okay, so I cannot run it there because I don't have the hardware, but I can generate it. Let's go back to AVX2, which is aplenty. So we have these kind of things, and we saw that we can generate something very meaningful in terms of results. Okay. Another way to fill up whiles is to use either a direct initialization by braces. It only works when you have the proper number there. So it's very architecture specific. The order is always a natural order, okay? Because some CMD registers are little Indian, some are big Indian. We don't care. We store them correctly every time. Okay. As we already saw, then you can also fill using a formula, okay? Either by having just the index of the current lane you want to compute, or the number of the ID of the lane and the number of lanes. So this is basically some kind of iota, and this is something that basically uses the total size to know how many things it can do. And so if we take that and we go back there, let's have a look at what kind of result we get. Yeah, if you execute it, that's important. Yeah, so we had 1, 2, 3, 4, as we expect. Then we have what? 2.3 times 1, 2, 3, 4, and so on. And we had 1 over 0, 1 over 0 over 4, 1 over 4, 3 over 4, and so on. And if I remove the size there, so we get 8 of them, we should get up to 7 over 8, whatever. Okay. And as I said, I can just, like ask for 32, for example, because we like that. Okay. Oh, yeah, sorry. If fixed. Yep, and we got all of that, okay, which is probably what we want to get. Again, we can actually take that, make a small function and see what's going on. Okay, let's call that generate. Okay, and just say that we return that. So just in case, because I don't know exactly what are your level in C++ and modern things. If you have an issue about the lambda syntax or whatnot, don't hesitate, and I can answer your question later. Okay, what kind of assembly do we have there? Yeah, basically, yeah. We know that those things are finite. They are compile time bound. So basically what Clang does is just load a bunch of constants. And we have 32 of them by pack of 8. So we have 1, 2, 3, 4 operations. Okay, if I ask for 16, I got like 2 of them. Somewhere. Yep, okay, we have 2 of them. And if I have less, I will have an XMM with less inside. Probably. Yeah, we just saw that. We have 0, 1, and nothing else. Okay. Or 0.5, sorry. Yeah. So it adapts again. Okay, and we can get those values easily inside the thing. Okay. So much for initialization. What do we have next? As we said, we have a bunch of operators, a lot, functions, a lot. You can have a look at the documentation if you want, okay? Because we don't have time to go over all of them. But most of the time, if you need it, it's there. If it's not, you can find an issue, and we will tell you where you didn't look for it. And if it's really not there, we are going to make it, no problem. So what can I do? So I have a bunch of wide there, so I can do this. I can add 4 to every C, so that's broadcasting 4 to every lane of C. I can also do that. So every operator has an infix function notation, so add, sum, mul, div, and whatnot, bton, bitor, so that they can support something that we are very proud of, which is our option system, okay, which is those strange square brackets on top of a function. If functions are actually not functions, they are objects, function, okay? So we use these tricks to add extra API on top of the function. So what does this mean? This bracket, A less than B, C4. Well, we are going to compute C plus 4 and put the result only where A is less than B. And where it is not, we are just returning the first parameter, which is C. We can do multiplication, and we can do what we call relative masking. Okay, we are going to ignore the first 2 elements of the computation. So we are going to have C times B everywhere except for the first 2 values. You can call function, and we have a bunch of semantic modifiers. We have a lot of them, but the most useful are those ones. You can ask for a saturated operation. So B and C are added together, but if you go over the max value or under the minimum value of the type, you get clumped. Okay. Either it's done by doing the computation, or on some system, you have an intrinsic for that. So it was important to access them through a high-level API. You can ask for being pedantic. That means that we are going to handle more special cases that we normally do in exchange of less performances. Okay. So we are going to handle the normals better, we are going to handle corner case better, we are going to get as much precision as the standard could get and whatnot. You can also ask for a value to a function to be called numerically, which means that we are going to ignore nans. Just if you have a nan, we return the other values, okay? And we have the row modificators, and now we have also a fast modifiers. That basically says the exact opposite of pedantic. We don't care about precision and whatnot. I just need to go the fastest possible. Row implies that if you have a single instruction way to compute this operation, but you lack precision or you lack corner cases, we are just going to call the intrinsics. Whatever corner case, we don't care. So you can go very fast, okay? And obviously, you can combine those because you can put as many brackets you can. And a bit later, maybe this year, I think, we are going to support C++ 23 conditionally, and you could use the multiple argument brackets operator. Let's have a look at that by putting some value into it and look at what kind of operation and result we got as soon as I get my cursor back. So let's go back there, okay? Let's just do that. So we have our list of stuff to test, okay? And let's actually put some values inside. We are going to play around with different architectures, so we are going to try to fill them using functions either instead of doing this. Okay. So also, because it starts to be a bit irritating, let's do some using namespace. Using namespace, Eve. So we have a bunch of integers. Okay. So let's say that we have a. So let's say that a is like 1, 2, 3, and whatever. So it's I plus 1. Let's say that b is what? B is, for example, 10 times that. So I could also do something stupid like this, for example. So we have a look at that. You could write something like this. It's not very good, but it works. And let's see. Let's say C requires the size because we are going to return C plus 1 minus I. So we are going to have like 4, 3, 2, 1 or something. So let's have a look at those functions, at those values first. Okay, let's have that. I will try to go slower there if you want to replicate the code on your machine, so you can have an access to that. So 1, 2, 3, 4, 6, 7, 8, 10 times that, and 9. Oh, okay, the plus 1 is not required. Okay, that's better like that. 8, 7, 6, whatever. Okay, so what do we want to do? Let's do C plus 4. Let's just jump a line. And C plus 4, as we expect, should be 12, 11, and whatnot. Okay. Let's do this mask thing. Okay. So we are not going the exact same one because it won't be interesting, but let's call add. Let's say that I'm going to add C and 4 if and only what can we do? A is lesser than 3. Something like that. Okay. And let's see what we got. Yeah, so we have 12, 11, and then we stop because now we are not less than 3. Okay, so maybe let's less than 5. Okay. We see that the computation stops. And we go to C. Okay, so now if I do that, for example, if I do it the other way around, whenever the comparison is false, we are going to get 4 instead of C. And then we get that. So we get this kind of control. As we said, we can also have multiplication. Okay. And so the question is, why do we want to have this masking things that low level available? Because on some system, it's basically the same cost of doing a mask operation than doing an operation. So it's very interesting to have access to those using a proper API. So C times B do whatever C times B does. Okay. And let's do mul. between C and B. And let's do it only if, or let's say, we ignore the last two. Let's do something different than what we have there, but just so we can see that. So we have a bunch of relative conditional, ignore first, ignore last, keep first, keep last, keep in between, and so on. So whatever the size, and that's where it's interesting, those relative masking adapt automatically to the size. I have 8 there, so the last two are not touched. If I go back to SSC2, for example, and we have like 4 values, and the two first are ignored. Okay, so that's an interesting way to do some masking. Okay. Now let's do the saturate addition, okay, which is another interesting things to do. So let's saturated. Sorry. Let's do B times B. Oh, B and B, for example, but it's not. It won't saturate. How much is that? 2 billions? Yeah, 3 billions? Right. Okay, I don't know. Oh, well, no, I know. Let's take the largest integers and try to add A to it. Okay. Or B, for example. So let's do that. Let's generate the biggest integer I can get. Well, I know how to do that. I have a valmax function that takes the type I want. I want to be the same type as A. Okay. And that will generate the constant with the maximum value of int. So we got these things. Why? Because if I add something to the maximum sign value, I will get back to the minimum negative value. But now I can ask for saturation there. So it's not very interesting, but let's do that. And what do I get? Yeah, I got the max one. So okay, let's do something. Let's valmax minus 2. So the first two can get in, but not the last one. Okay. Oh, it's not probably enough. Yeah, okay, yeah, we get it. So we have a 46 and a 47 and whatnot. So we have a bunch of constants like that with this as function. So the question is, what is valmax actually? Because we just use it, but we don't know. So I want valmax in the same type as A. Okay, that's the way we read that. And it is whatever. So obviously, you see where this is going. We have valmin. We have very interesting constants sometimes. What's the name for that? Yeah, that's probably, yeah, we don't have many much there. I mean, the integral constant, there are not much. We are going to see what we can do with the floating point numbers. So let the thing compile. So we have the minus, the zeros, the whatnot, and so on. So now if we have a wider float, which is more interesting, let's say it's just return, I don't know, 1 over I. Okay, and let's have a look at what we have there. Okay. Yeah, we have a missing semicolon, as usual. Again, I mean, if you want to test that, you can have a look at the code and try to replicate that. So we have 1 over 0, 1 over 1, and so on. Okay. So what can we do? Oh, well, we can generate some interesting constant. So we can have minus infinite as x. We can have mantisabits of x. Let's have a look at that, for example. And we have a bunch of that. Oh, is it mantisa? Not mantisabits? Mantisabit? Ah. Okay, I forgot where they are, obviously. So let's go to the documentation. Oh, mantisa mask, obviously. Yes, mantisa mask. That's the one I want. No, that's not the one I want. This is a lie. Okay, let's look for oh, NB mantisabits. Okay. Yes, that's better. NB mantisabits. number of mantissa bits in a given values. So for float, it should be 33, if I'm not mistaken. Am I? I'm not. Okay. So we have those things. Okay. We have also a lot of EEE related function. So what do we get? Yeah, we got x, mean, square root, and whatnot. Okay, we could have a look at that. But by example, we can get that. So, before I write something stupid, let's have a look at the documentation. Is it FRX? No. LDX? LDX. Is it? Oh no, LDX is this one. So it's not the one I want. I want the other one. It's not. Okay, I don't know. So you know what? Let's see if I find it somehow. It's probably in core functions, EEE set font for operation. So what do we have? Byte of sign, exponent. If FRX. That's the one I want. Okay, yeah. For some reasons. So what does it do? Again, before doing something stupid. EFRX. Yeah. So it slice. Compute the mantissa and the exponent. So I want the mantissa as the exponent, and I want EFRX of x. And so I can have a look at the mantissa and the exponent. So that's for the people over there that do maths. They like to do tricks with the EEE 754 representation. Yeah, and I got what I got. It's probably correct. I don't know. Yes, 129 for if and whatnot. See how we can structure bind the result, but we could also have the thing as a single value, normally, and that will be in for later. And we have some sort of wide of pair. And yes, it is exactly a wide of pair, which is actually stored as a pair of wide because that's the way to do it. And this is one very important point. If you want to have a list of silent differences between all the other library and Eve have a natural support for data structure. We are going to see that a bit later, but you can have a white of some tuple if you want, and you can do whatever you want with the parts. And it's naturally stored in a SOA order, so we can get proper performances. And so on and so forth. And we can play around with all those functions and operation this way. Okay, so what's next? We also have something which is very important to understand, which is the shuffling operation. As I said, you can look at register as some sort of small arrays in the hardware. And one operation sometimes you need to do is to shuffle around the value inside the register. So if your register is 1, 2, 3, 4, you can shuffle it to be 2, 4, 1, 3. Okay. Either by using a pattern, but it's not very portable, or by using a pattern function. Okay. So you compute some reorganization of your things. And sometimes you have what we call a name shuffle or name swizzle that lets you actually apply some correct operation on that. So you can reverse the value and so on. So what is the usage of that? Sometimes you are going to want to load data, but they are not in the order you want for the operation to make sense as an SCMD operation. Okay, right? So you are going to try to load that in a bad manner. Okay. So what you are going to do, okay, is to load your data badly, as they are, okay, and find a way to reorder them, okay. For example, if you do computation over sparse matrices and whatnot, okay, you can get use of this thing. This is a more advanced element in the API. Okay, so we are going to pause there. It's almost 1 hour and 30 minutes. Okay. As I said, you can ponder, play around with the documentation if you want, and how to say that? Play around with the documentation, play around with the function, try things and break stuff. You have a mat.cpp file that you can actually play around with in the container, so you can play around and have some actual measures of performance of our operations. You are going on a break, and after the break, we are going to speak about algorithms and more complex operation over data. Okay, so enjoy your break, enjoy playing around with the library for now, and we are going back in a couple of minutes. See you later.